In the 1960s, during the space race, the field of space exploration was born, and although development has slowed down since then, the fields of rocketry, spacecraft, and space launch systems are to this day incredibly interesting fields. Today, I'm going to be explaining the Rocketry and Spacecraft Iceberg chart. Let's get started! On July 16, 1969, a thunderous sound was heard from the beaches of Cape Canaveral. The Saturn V rocket has just lifted off, officially launching the Apollo 11 mission. At T plus 13.2 seconds, the Saturn V rocket begins to roll to a degree of 72. Launching directly towards the moon would be ineffective, so instead the Saturn V orbits the Earth and then expands its orbit towards the moon. T plus 2 minutes and 42 seconds. The first stage runs out of fuel and is separated from the rocket. The second stage takes over and continues the trajectory right until T plus 9 minutes and 8 seconds, where the second stage runs out of fuel and is too separated from the rocket. The rocket is almost in orbit around the Earth, but is not quite there yet. The third stage takes over, continuing the burn until T plus 11 minutes and 39 seconds. The third stage engines shut off and the Saturn V rocket, along with the 3 astronauts inside, have successfully reached an orbit around the Earth. But Earth is not the destination. The crew must still perform the translunar injection to expand their orbit if they want to reach the moon. At T plus around 2 hours, the third stage ignites, putting the vehicle and the 3 astronauts directly on a trajectory towards the moon. Before the crew may rest, however, they have one last task. Currently, the rocket contains the CSM where the astronauts currently are, and below that, the Eagle lander. The CSM is not connected to the Eagle lander, which it needs to be to continue the mission. To fix this, the CSM separates from the third stage, turns around, and docks with the Eagle lander to grab it out of the rocket. Now comes the less exciting part, the wait. Apart from some mid-course corrections, the crew must now wait until they reach their destination. Time passes. The moon is now visible from the capsule. The vehicle is going very fast, and at this rate the astronauts will fly right by the moon. They need to decelerate if they want to orbit the moon and not fly by it. At T plus around 76 hours, the engines are ignited, and once the burn is over, the vehicle is in a stable orbit around the moon. Neil Armstrong and Buzz Aldrin are transferred to the lander, leaving Mike Collins behind in the CSM, and some hours later the lander is separated from the CSM. A little later, the Eagle lander starts its burn and is on a trajectory to land on the moon. The lander is getting closer and closer to the moon. A mere 15,000 meters above the moon's surface, the Eagle lander begins its final burn, and at T plus 102 hours, touchdown.
It's one small step for man, one giant leap for mankind.
On July 21st, 1969, approximately 22 hours after the landing, the ascent stage of the Eagle lander lifted off, leaving the descent stage on the moon. The 2 astronauts would now dock with the CSM to continue their trip home. To do this, the astronauts would have to match their orbit up with the CSM to rendezvous, and once they did, they had to align the 2 vehicles perfectly together. Once the 2 vehicles were docked, the ascent stage was jettisoned and the CSM, now with all 3 astronauts, would ignite its engines for a trans-Earth injection. Once more, the crew had to wait. This time they were on a trajectory towards Earth. They had successfully landed on the moon, but now remained the most dreadful part of any space trip, the re-entry. At T plus around 195 hours, the capsule separated from the rest of the rocket. Around 13 minutes later, the capsule goes through the atmosphere. The G-force exerted onto the astronauts is now 6.56, as the capsule is getting deeper and deeper into the atmosphere and is decelerating more and more. Approximately 9 minutes after entry, the drogue parachutes were deployed, and at T plus 195 hours, 18 minutes and 35 seconds, splashdown. The 3 astronauts had made it home safe after their trip to the moon, and would now be put in a quarantine facility to ensure they didn't bring any deadly, unearthly moon sicknesses to Earth. After the success of the Apollo 11 mission, 9 new moon landings were planned, but in the beginning of the 1970s, the importance of space exploration was put into question. The United States had put an American on the moon before the end of the decade like they promised, and with the US finally somewhat ahead of the Soviet Union, NASA's budget was cut and 3 of those planned moon landings were cancelled. As for what happened next, the Soviet Union and the US would kinda just do their own thing, making space stations, satellites and whatnot. And in 1975, the two superpowers carried out a joint mission wherein the American Apollo module docked with the Soviet Soyuz capsule, which many see as the end of the space race. But what's next for human space exploration? Well, NASA is currently planning the Artemis program, which will send humans to the moon again using the SLS Rocket. The SLS Rocket is a super heavy lift rocket currently under development with a payload capacity of 95 tons to low Earth orbit. The first launch of the SLS, Artemis 1, is planned for November 2021, and hopefully the Artemis 3 mission, planned for October 2024, will land on the south pole of the moon. The SLS rocket is, however, not the only attempt to create a rocket that can go to the moon. SpaceX is currently developing the SpaceX Starship, which will have a payload capacity of about 100 tons to low Earth orbit. As of March 2021, when I'm writing this script, the Starship is currently being tested, and while there are no solid plans for an orbital mission as of yet, SpaceX expects the first orbital flight in 2021 and a flyby loop around the moon in 2023. Okay, quick update. I took so long making the video that there are a couple of updates regarding the Starship. The 16th of April 2021, NASA announced that they contracted SpaceX to develop a modified Starship as a lunar lander for their Artemis program. So, Brezhnev, remember Space Shuttle that Americans make? Yes, what about it? I looked into it and the Space Shuttle would be more expensive for Americans than the rocket it is supposed to replace. Okay, that just sounds like stupid American doing stupid thing. Yes, well that's the thing. Space Shuttle will give Americans ability to launch 1,500 tons of stuff into space every year. Why would they need that much? I've looked through the files, and it's very possible that motive behind the space shuttle is military. Did I mention that it has ability to take things back from orbit? The Soviets were getting concerned over the true motive behind the American space shuttle and decided to make a shuttle themselves. It had to be, at the very least, as good as the American shuttle if they wanted to compete, and so they began work on the Buran space shuttle. The two rockets looked remarkably similar, but you see there was a couple of key differences. On the space shuttle, the main engines weren't enough to lift the rocket by itself, which is why 2 side boosters were needed. The Soviet Buran shuttle, however, was lifted by a rocket called the Energia. This was a separate rocket, which meant that it could launch without the Buran attached. On its own, the Energia rocket would carry 100 tons into low Earth orbit, which is even more than the N1 they planned to go to the moon with. Despite the Soviet Buran being arguably better than the American space shuttle, it only had a single launch the 15th November 1988, which proved to be successful. The Soviet Union had plans to use the Buran shuttle again, but the dissolution of the Soviet Union meant that the Soviet space program got its funding cut and the rocket was never used again. As the field of rocketry and space exploration progressed in the 1960s, rocket scientists were excited for what would come next. Different plans for space stations, extraplanetary outposts and powerful rockets were conceptualized. Among those was the Sea Dragon. The Sea Dragon rocket came from the idea that as the field of space exploration advanced, larger and larger payloads would be made, and rockets would have to be more powerful. Larger and complex rockets would, however, become awfully expensive to make, and so Robert Truax had the idea of making the rocket very simple but very large. Turning this idea into an actual rocket design, Truax had the idea of launching the rocket from the ocean, hence where it's got its name, Sea Dragon. The Sea Dragon is the largest and most powerful rocket ever fully designed. It was, however, never produced since there was never really any demand for a rocket capable of 550-ton payloads, and after the discontinuation of the Apollo missions and the collapse of the Soviet Union, progress in the field of rocketry stagnated. SSTOs are rockets that can reach an orbit without throwing any stages away. Currently, there aren't any rockets that have been able to do this from the surface of Earth. Why? Well, let's say we have a satellite we want to put into an orbit around Earth. Let's build a rocket that can do this. No problem, the satellite only weighs 50 kilograms, so we'll just make a rocket that can put 50 kilograms in orbit and wait, now the rocket weighs more. So I guess we need the rocket to be even bigger so it can lift itself. But now the rocket weighs even more and needs to be even bigger to be able to lift itself. Huh. In other words, SSTOs are hard to make, and when we try, we often end up with a lot of rocket and little payload. This is why rockets often have multiple stages. By having multiple stages, the rocket throws away its empty tanks, lowering its weight. Now, I know what you're thinking. Well, if that's the case, why are scientists even trying to make SSTOs? Well, throwing away huge rocket engines and expensive fuel tanks is not cheap. Imagine if we threw away airplanes after use. So what can we do if we want to make a usable SSTO? It could be done by having more effective rocket engines. There have actually been multiple attempts at making an SSTO, like the DCX by McDonnell Douglas, the Shuttle Serve by Chrysler Corporation, and the Aquarius by Space Systems Loral and Aerojet. If you thought going to Mars was hard, just wait till you hear about interstellar travel. If you want to travel to another star, we have to be creative with our solutions. A regular rocket that accelerates just once would take forever to reach another star. If we, on the other hand, constantly accelerated, the entire process would be much faster. Solar sails are an attempt at just this. They work by having a large sail that uses the energy of sunlight to propel itself. A solar sail with a length and width of 350 meters would get a constant acceleration of 1 Newton. This doesn't sound like a lot, and yes, it is comparatively low, but compared to the fact that it doesn't use any fuel and can reach the speed of light in only years, then this is pretty good. The only issue, of course, is the weight constraints. So let's explore some other potential interstellar technologies. Project Orion, not to be confused with NASA's crew vehicle Orion, or the American sounding rocket Orion, or the Orion satellites, or the Orion rocket stage, or the Orion space telescope, or the Orion rocket, was an idea for a theoretical rocket that would use atomic bombs as propulsion. This was interesting because, unlike most conventional rockets, it would have a constant acceleration. If we had made the Orion work, it would have a constant acceleration of 1g, and it could even reach Alpha Centauri, the closest star to ours, in only 133 years, which is still a long time, but if we accelerated faster than that, we would exert more than 1g on the passengers inside, which would be pretty rough. I mean, if only there was some other theoretical spacecraft with faster than light travel without all the issues of acceleration. Perhaps some warp drive? Things in the universe cannot travel faster than the speed of light. End of sentence, we cannot go around this. But the universe is flexible. Space-time can contract and bend, in fact it constantly does. Gravity is a curvature of space-time. Where there is mass, space-time is curving. Okay, let's make an analogy. Let's say this string represents 1 light year. If we followed the string the entire way, we wouldn't be able to get to the end in less than a year. But this string, representing space-time, can curve, expand, and contract. What we could do is that we could have a spaceship with a bubble around it, where we contract space in front of the bubble and expand space behind the bubble. This would move the spacecraft forward. It's kind of like imagine we have a tunnel, right? And we just want to go through it, but it's super long. So instead of walking the entire way, we kind of just do this, right? Why try to go the speed of light when we can just make distances shorter? And then to ensure that we aren't squeezed when the tunnel is made smaller, we put a bubble around us that protects us. This is the idea of the Alcubierre drive, but instead of it being a tunnel, it's space. Okay, I know what you're saying. Yeah, sure, contracting space is super easy, it just requires matter. But how the do you want to expand space-time? Wouldn't that require negative mass? Right, yes, it would. You see, the Alcubierre drive abides to Einstein's field equations, but that doesn't necessarily mean it's possible to make. We would still have to discover matter with a mass lower than that of vacuum, negative mass, also called exotic matter, which is a theoretical form of matter. Okay, pause. Quick update. So actually, while I was animating this video, someone published a paper about how you can make a warp drive without exotic matter. I'm not going to go through this in this video because it's really complicated, and by the time I'm done animating that, someone will have made a new paper about Alcubierre drives, but it looks like there's still some hope for this technology. Anyway, let's move on with the video. The launch loop was an idea by Keith Lofstrom to launch objects into orbits on what is essentially a giant slingshot. The launch loop would function by having an enormous cable system with a height of 80 kilometers and with a length of 2,000 kilometers. The launch loop would use maglev cables to accelerate an object to orbital speeds. Unlike the space elevator, we don't need some theoretical super strong and tensile material to make the launch loop. This is something that could be done today if the demand for orbital payloads increases significantly. Let's say we're launching a rocket on Earth. Gravity is constantly pulling the rocket down, and so the rocket not only needs to accelerate, but it also needs to lift itself up. This means that there is some of the lift being wasted on combating gravity. This is called gravity loss. The amount of gravity loss is minimized the smaller the amount of time the rocket engine is firing. Typically, we don't really think about this too much when launching a rocket here on Earth, since if we add more thrust than necessary, the rocket will experience a lot more drag, making it more inefficient. We do, however, care when landing a rocket. Take the SpaceX first stage boosters for example. The boosters needs a bit of fuel to land so that they can be reused. However, we want as much of the fuel as possible during the launch of the actual rocket. This means that the landing has to use as little fuel as possible. Instead of turning the engines on a low throttle for a nice and smooth landing, doing a hard landing at a high throttle right before the vehicle hits the Earth is actually more effective. This is called a Hoverslam. A space gun is a way of launching, or rather blasting, an object into space. A space gun, like the name implies, uses what could arguably be called a large ballistic gun or cannon. Space guns have a number of advantages over regular rocketry, the most notable one being that it's super cool. I mean, it's literally a huge cannon launching payloads into space. One of the issues with space guns is that all the acceleration happens at once, which can be an issue because this slows down the object significantly due to drag, but also exerts enormous g-forces onto the object. This slows down the payload significantly. Surprisingly, this idea has been attempted many times, like for example Project HARP, which successfully made a space gun that currently holds the world record for the highest altitude for a gun-fired projectile at 180 kilometers. Let's say we want to go to, I don't know, Saturn, but our orbit is like this, while Saturn's orbit is like this. If we were to go to Saturn normally, we would expand our orbit like this, but is there a way of doing it more effectively? The answer is yes. What we can do is that we can utilize the gravitational pull of a planet, moon, whatever, to gain speed and change our trajectory without using fuel. This is called a gravity assist.
But how does it gain speed? Doesn't that defy the laws of conservation of energy?
No. Why? Well, when the spacecraft approaches Jupiter, it accelerates. But when it leaves Jupiter again, it decelerates. This means that the spacecraft simply changed the direction of its trajectory and hasn't gained any speed relative to Jupiter. A gravity assist can, however, increase the velocity of a spacecraft relative to the Sun. Imagine you throw a ball at a moving train. The ball will bounce off the train, and from the perspective of the train driver, the ball hasn't gained any additional speed. The ball departs with the same speed it had when it arrived. The ball does, however, gain some velocity from the moving train relative to the person that threw the ball. This is similar to how gravity assists can increase the velocity of a spacecraft. After the success of the Apollo missions and the astonishing Saturn V rocket, many rocket scientists were wondering where to go from here. Many new ideas for how to utilize the Saturn V rocket came about, and one of these was the Saturn-shuttle, which was just a Saturn V rocket with a space shuttle on. In the 1970s, the German company OTRAG started development of the OTRAG rocket. The concept of the rocket was different from other rockets at the time. The concept was that the company would mass produce the individual tanks of the rocket and then combine them. The idea was that the mass production of identical tanks would bring the price down significantly. The OTRAG had a successful test launch in May of 1978, but the rocket's third test failed in June of that same year, and the company experienced fairly heavy political pressure to stop their operations. The company moved their operations to a site in the Sahara Desert in Libya, and although they did manage 14 test launches from their side, the rocket was never commercialized and the company went defunct in 1987. The Roton was a rocket concept developed by a rotary rocket company. The idea for the Roton was initially to have an SSTO that is first lifted by helicopter rotor blades before firing the engine to push the rocket into orbit. The idea was, perhaps somewhat misleadingly, called helicopter to orbit. The idea was later revised as the helicopter rotor was calculated to not really increase the effectiveness of the rocket. Instead, the rocket would use the helicopter rotors to land again after returning from an orbit. The Rotary Rocket Company was formed in 1996 to develop the Roton. The company gathered $33 million to develop and commercialize the rocket. The Roton had 3 test flights in 1999, but the company ran out of funds in 2001 and all development of the rocket has stopped. World is Not Enough, we'll just call it WINE, is a joint project currently under development by these universities and companies to make a spacecraft that can mine the ice off the surface of an asteroid, a moon, a planet, whatever, to collect water, which it then uses as fuel. It would do this by heating up the water to create steam, let the steam escape, and boom, you've got thrust. The WINE is particularly interesting since it can, in theory, explore space forever, hopping from asteroid to asteroid. USAF Project A119 was a plan developed by the United States Air Force to, of all things, nuke the moon. The idea was that it would reveal a lot about the material composition of the moon. Also, the crater and explosion would be visible from Earth, making it a huge flex on the rest of the world. The plan was revealed in the year 2000 by a former NASA executive. As ridiculous as this plan may sound, the Soviets had the same idea for a project like this, which they also started development of in 1958. Congratulations, you're finally done with the video. I hope you liked it. I want to thank user AlphaCoronae on Reddit for letting me borrow a few entries from their iceberg chart. I also want to thank all of you for the amazing support I got in my last video. I never expected that video to get that many views. When I started working on this video, my first video had less than 100 views, so I didn't spend so long making this script since I didn't think I would have much of an audience. A while later though, I decided to rewrite parts of this video, which is why it took me so long to make. Also, did you know only 0.7% of my viewers